Hello, everyone, and welcome to this free webinar series presented by WePassed. My name is Christina Ruiz, and I will be your moderator this evening. Throughout the webinar, we will stop the presentation to review. There will be multiple choice poll questions, which you will be able to answer in the sidebar. Please go ahead and answer these questions as they come up. You will have about 1 minute to answer the question before we go over the answer. During the webinar, please feel free to use the chat window to ask questions and discuss the topic. We will take time after the presentation to answer these. This and other recorded webinars will be available to WePass subscribers. Register through wepass.com to become a subscriber. Tonight's topic is titled Therapy Room Shielding Using NCRP 151, presented by Jim Rogers, PhD. He is a director of physics for the CyberKnife at MedStar Franklin Square Hospital, a position that he has held for the last 10 years. Thank you for joining us, Jim.
Well, thank you, Christina. And good evening to everyone out there. This is a topic that most people don't get too much opportunity to participate in. And so it does get stale unless you use it, and the review is definitely in order. And so we'll get going here. I've got a fair number of slides, so I want to try to keep on schedule. The basic things we're trying to do is protect people both inside from when they're in there and as well on the outside. Often this inside is from adjacent rooms, but most important is the area outside of the vault. And there's three basic types of radiations that are in that room being produced by some kind of a source, usually a linear accelerator. The primary beam hitting the primary barriers, the patient scattered radiation, and the leakage radiation coming out of the waveguide and the bend magnet and the targets and other areas. As you all know by this point that the three critical factors for reducing radiation are time, and distance away from the source, and the radiation shielding. Radiation workers are those that are occupationally exposed and those that can possibly receive more than 10% of the applicable annual limit of radiation in a year. And these people, radiation workers or occupationally exposed, basically must wear a personal dosimeter to be able to account for what they receive. Members of the public or employees who are not deemed to be radiation workers do not need to wear a dosimeter. Time in shielding is based on a 40-hour week. The occupancy factor, T, is the fraction of that 40-hour week that an individual would be near a source of radiation or in a particular area. And T is called the occupancy factor. Members of the public are those people that enter uncontrolled areas, or often called unrestricted areas, and can spend as much time as they want to in that area. We have no say about that. However, this time is usually not more than 40 hours per week. That's the assumption. If it's going to be more than that, some adjustments to the calculational procedures will need to be made. Individuals who spend the greatest time around radiation sources are usually those people just outside of the vault or the shielded area that have offices outside of those areas. And they are generally there 40 hours a week. There are radiation areas which are inside or outside of the treatment room and can be categorized either as controlled or restricted areas or as uncontrolled or unrestricted areas. A controlled area has a restriction on access to it. It can be signs, could be verbal communications, could be gates and locked doors. So what is this applicable annual limit that 10% of which determines classifies you as a radiation worker. It's basically the whole body radiation total effective dose equivalent per year, which is set by international and, more importantly, US standards at 50 millisieverts. So 10% of that would be 5 millisieverts in a year, and that's the action level for declaring a person a radiation worker. Some of the other applicable limits you've probably seen before are dose equivalent for the eyes, particularly the lenses, the extremities, 50 millisieverts, skin, and another one that comes up frequently is the declared pregnant worker, which is set at 0.5 millisieverts per month. So in this presentation, I want to try to stick with using the same kind of unit throughout, either the millisievert for dose equivalent or the milligray for dose or gray, and we'll use sieverts as well. So we've got these three quantities which are often expressed in state regulations in terms of rem. So the equivalents of the rem and the millirem and the millisievert are there in this chart. I'm sure most of you have seen that. And the next question is, where do the regulations and guidelines and suggestions come from? It's important to know this, where they come from. The National Council on Radiation Protection and Measurements, called the NCRP, is a federally chartered organization that establishes recommendations and guidelines for radiation protection limits and basically makes these recommendations to the public and to law enforcing organizations, but their recommendations are not laws and are not regulations. Individual states and the NRC are empowered to establish regulations and enforce them. The Nuclear Regulatory Commission establishes regulations for protection of radiation that's coming out of radioactive materials. Most, in particular, ones produced by nuclear reactions and often referred to as nuclear reactor byproduct materials. The NRC does not, as of this date, regulate electronically produced radiation sources. Linux, X-ray sources, and so on are not under the NRC jurisdiction, but they have from time to time tried to make that the case. The NRC enforces its regulations in all states and territories, except those that have an agreement with the NRC to promote and enforce their own regulations. And the NRC also controls by the licensure process. Either you get it or you get it taken away. The 37 agreement states enforce their own regulations. And their regulations must be at least as restrictive as the NRC's. Agreement states as well issue licenses based on qualifications and safety programs of the applicant. Now, there's another party involved here. It's called the Conference on Control Program Directors. And generally, agreement states adopt the suggested state regulations for control of radiation, the SSRs. And these are developed by the Conference on Control Program Directors. The suggested state regs extend their applicability to most sources of ionizing radiation, in particular imaging equipments and LINAC. Non-agreement states basically let the NRC oversee their NRC licensees on nuclear byproduct materials, and these states adopt their own regulations for other sources of ionizing radiation, such as LINACs. The current recommendations and NRC regulations on the maximum permissible cumulative annual dose equivalent for individuals exposed to ionizing radiation are summarized in this table. And these are often referred to as maximum permissible dose equivalents, or MPDEs. Under the recommendations here, the NCRP recommends 50 millisieverts per year for occupationally exposed and 1 millisievert per year for the public. That's the same as the NRC, no surprise. And I point out down here at the bottom that natural background radiation, not including medical, is about 1 millisievert per year. So the public is basically allowed to get another dose of natural background, average natural background. When it comes around to shielding, the NCRP has basically looked at, well, if you're designing a facility, you don't necessarily want to design it to the limit, at least for the occupation, the controlled areas. And so they have a quantity called the shielding design goal, or the shielding design goal limit, labeled P. And this really applies to controlled areas. And in this table here, we see that the controlled area limit has been dropped by a factor of 10, whereas the unrestricted or uncontrolled area remains the same as it is in terms of the applicable regulatory limit. That's because it's really hard to get down below natural background. Whereas this 10-fold reduction means that there's only a 5-fold difference between controlled area limits and uncontrolled. Again, these are design goals. And in radiation shielding, it's kind of a matter of tradition, not necessarily anything better than that we work with weekly limits in our design. So we divide the annual by 50 to come up with the weekly p-values, 0.1 millisievert per week for controlled and 0.02 millisievert per week occupational, uncontrolled or public limits. Radiation shielding designs also always follow the ALARA concept, as low as reasonably achievable. And basically what that says, if it's financially feasible, adding additional shielding to bring this design down even a little more is what they would recommend, as low as reasonably achievable. And often that translates into adding an extra half-value layer of shielding material. It somewhat depends on how the designer went about designing too, in terms of whether they need to do that extra step. They may have made it into their calculations from the very beginning. But I want to point out that these shielding design goals are not necessarily law per se. So it won't be a violation of regulations if the radiation survey finds that a controlled area, in a control area, the expected annual dose equivalent is higher, let's say 50% higher than the design goal of 5 millisieverts. That's because that design goal is a bit of guidance, but it isn't regulatory. And again, the regulations are annual values so that you can have weekly variations and still be fine in terms of the annual cumulative dose to any individual or in a particular area. Finally, the FDA gets involved in setting regulatory constraints on manufacturers of equipment producing ionizing radiation. In particular, the limit on leakage radiation from the source or head of the source or the collimating devices is set by the FDA. And NCRP is involved in that in the background by setting recommendations for the FDA. And NCRP Report 102 is an example of that. All right, Christina.
All right, here we go. So the first poll is up and live. For those of you who are just tuning in now and didn't get to hear the announcement earlier, if you'd like to, you can go ahead and join in our poll on the left-hand side of your screen. Take a moment to answer it now, and in about a minute, I'll have Jim go over it. And Jim, if you'd like to just read over the question now, I think that would be great.
All right, yes. So what is the annual MPDE for radiation workers and for members of the public according to NRC regulations? A is 100 millisieverts and 10 millisieverts, 5,000 millisieverts and 500 millisieverts, 50 and 1, or 10 and 1.
All right, great. So let's just give everyone a few more seconds to go ahead and answer the poll. We'll only have the poll live for a few minutes. Hopefully there isn't too much of a delay in the screen, because we'll be ending the poll shortly and going over the answer. So Jim, either everyone's getting it right or not a lot of people have weighed in, so I'm not quite sure how to tell. But looks like C was the overwhelming majority. Can you go over the answer?
Well, that's good, because that's the right answer. Okay. Yeah. I think the B answer is more familiar if you're dealing in millirem, so the units could throw you off there. And D is what NCRP's p-values are close to, but not exact. Yeah, C is the correct regulatory limit. And I've got here some additional questions, but we won't have time to go over them, but you might want to take a look at them if you have a chance to look at this later. I think that was it on those. So I'll give you a second to take a look. If there's one of them that stands out, is like, what in the world is he saying? Let me know. Okay, let's move on. Radiation shielding formulas for calculating the expected dose beyond the barriers are what we're going to look at next. And what kind of barriers do we have? Well, there's two primary kinds of barriers. We've got the primary barrier for the primary beam. It's always going to be thicker. And then we have secondary barriers for the leakage radiation and all the scattered radiation incident upon that barrier. So these secondary barriers are generally significantly thinner. The layout here is one where we've got a maze and a door at the end of the maze, and this area here has a secondary barrier. It's protecting the door over here, and a primary barrier. For the primary barrier shielding, the thickness is what we want to determine, and we basically set the expected dose equivalent, this quantity here, with a barrier factor, transmission factor in there, to be equal to or less than the design goal, P. So the first thing that's important to remember in doing these kinds of calculations is to get all your units consistent, and the design goal should be expressed in the same units and time period as the workload up here, P. So what is this formula says? It's the barrier transmission factor times the weekly workload of the primary beam, times the use factor for the beam pointing at that particular barrier, the occupancy factor for individuals on the other side of the barrier, and the inverse square of distance from the source through the isocenter to the protected location. The barrier transmission factor is labeled with a PRI because there are different barrier transmission factors we're going to be talking about in a minute. And the, oops, I seem to be missing this. Okay, no, I just repeated this. Sorry, confused by my own slide. The primary barrier workload is the radiation at 1 meter, for Linacs anyway, from the X-ray target and expressed in dose per week. The final units, because it's at 1 meter, should really be written as in gray meter squared per week or milligray meter squared per week. And again, we want to make the p-value we use consistent with the units in the workload. Otherwise, you could be off by several orders of magnitude. So our aim here in this calculation is to determine the maximum required value of the barrier transmission factor, and then to use that value to determine the minimum barrier thickness that will satisfy our design goal, P. So we get a thickness from this B. How do we do that? The attenuation factor B, or the transmission factor, for photons and neutron sources is usually expressed in terms of the number of half-value layers or tenth value layers, TVLs, that are needed. And that this here expresses that in terms of half-value layers, the number of half-value layers, or 1/10 times the number of tenth value layers. The number of tenth value layers is basically the thickness divided by the tenth value layer value, which is something we just tabulated. This gives us how many basically orders of magnitude we need to attenuate to bring that radiation down to acceptable levels. For radiation shielding, we always use broad beam data, which is not what is often specified or measured when you're trying to specify the quality of radiation. Quality of radiation is usually based on a small beam, whereas shielding radiation, TVLs and HVLs, are appropriately specified for broad beams because of all the scatter that goes on in the barrier as the radiation is transmitting through, and it increases the amount of radiation on the far side, having a broad beam. So secondary barriers attenuate two kinds of radiation, as we said before, the leakage radiation from the head of the machine and patient or wall scattered radiation. We're going to focus on patient scatter here, but wall scatter is, we'll talk a little about that later. The main thing is that these two kinds of radiations have significantly different qualities in terms of their penetrating ability through the barriers. They have different workloads and different formulas involved. So for leakage radiation, we calculate the leakage barrier transmission factor, BL, from this formula, which is very similar to the one before. The main difference here is we've got a leakage radiation workload, and the distance is taken to be from the isocenter, not the target. And there's an extra little factor, F, here. So BL is the barrier transmission for leakage, and leakage radiation is normally fairly close to primary beam radiation. If you don't have a table of TVLs for leakage radiation, you would use the primary and you'd be on the conservative side. F That little f is the fraction of the primary beam at 1 meter that is transmitted out of the LINAC anywhere along at a meter away from the electron beam path. And by FDA regulation, this should be less than or equal to 0.1% of the radiation or useful beam at 1 meter. So F is 10 to the minus 3, and you can use a more conservative value if you can guarantee it, so to speak, that the manufacturer has shown you for sure, like it might be 0.5 times 10 to the minus 3. So leakage radiation emanates basically in all directions, away from the accelerator waveguide and the target and flattening filter. And because of that, at most points around the room, you can actually use the isocenter as kind of the center of leakage radiation. That isn't always the case, and actually there is anisotropy. It's lower in the back. And if you're really concerned about the ceiling, you might be concerned about the fact that when the head is pointing down, the gantry is pointing down, the head, the source of leakage radiation, is much closer to the ceiling than when the beam is horizontally or pointing up. And that can be taken into account. But for most locations in the room, the isocenter is taken as the source or the origin for leakage radiation. For leakage radiation, we normally say that the use factor is 1 because it's so isotropic in terms of where it's going all directions pretty much equally, but not truly. Okay. The workload, though, is the average. For leakage is the average radiation workload, and it's directly proportional to the number of LINAC or radiation source monitor units for the primary beam to deliver a dose at 1 meter from the source point. So if you've got a simple unmodulated beam, the radiation, the leakage radiation workload and the primary radiation workload are essentially the same. On the other hand, today's technology has very much gone to modulated radiation beams, and the modulation increases the number of monitor units to give the desired dose to the target volume. So if, for example, F is the fraction of patients treated with something like IMRT or rapid arc modulated beams, then the leakage radiation workload is going to be the primary workload times a factor which is basically the number of the percentage of treatments that do not involve modulation times the fraction that are being modulated and a so-called modulation factor. This modulation factor, it really is the measure of how many extra monitor units are required per centigrade to achieve the dose at isocenter. So it's often referred to as the MU per centigrade ratio. For rapid arc and IMRT, this modulation factor ranges from 3 to 5, and it gets up 10 to 15 or 16 for the CyberKnife, and for tomotherapy, it's even a little larger, since these are heavily modulated beams. Leakage radiation is usually the main determinant for secondary barrier thickness, and the exception is that near the edges of the primary barrier. The patient scattered radiation is basically radiation that's going into the patient, being scattered out of the patient, at various angles. I'm going to give you a quick picture here. We've got the radiation source over here, the patient, and then scattered at some angle theta is the scattered radiation, and it penetrates this barrier to the location being protected. So this formula for the barrier scatter radiation barrier transmission factor, how we determine that is we set all of this here equal to our design goal. Again, we've got the primary barrier workload involved here because what hits the patient is directly proportional to what's at isocenter. A use factor for that direction where the scatter is going, an occupancy factor, distance from the patient to the isocenter, usually that's 1 meter, and a factor called A theta, which is the fraction of radiation dose incident on the patient. It's actually scattered at angle theta. And then there's a field size dependence factor here. And most of the time we take this to be a 20 by 20 field so that the area is 400 square centimeters, and this factor becomes 1. Only for very small or very large fields would you need to deviate from that being just 1. All right, so again, theta is the scatter angle, these distances, the distance d SCA scatter is actually from the patient isocenter to the location being protected. And I think the important thing here is this fraction of radiation scattered is very directionally dependent. It's very strongly, and the quality of radiation is also. So if we go and look at a table of scattered radiation showing its TVLs, you'll see that it's very much directionally dependent. And the most forward directions were small scatter angles up to around 20, 25 degrees. That's the most penetrating radiation for scatter, most penetrating scatter radiation. And that is really important for the higher energy beams, that radiation that's scattered in the smaller angles can be as penetrating as the primary beam. And due to the fact that Compton is the dominant scattering mechanism, when theta goes over to 90 degrees, the maximum energy of the scattered energy spectrum is 0.51 MeV. So no matter what you started off with, at 90 degrees, you've got a fairly low energy beam. And at 135 degrees, it's even lower. So as a result of this fact that the two types of radiation on secondary barriers are not equivalent in energy, let alone strength, you can't just add them up and determine the total radiation on incident on the other side of the barrier without the barrier. You basically need to determine the barrier thicknesses required for each one independently and then combine them using the two-source rule. So what is this two-source rule? The NCRP came up with this a long time ago in NCRP 47. I think it was even prior to that, 33. But anyway, they came up with this rule as a conservative process for combining barrier thicknesses determined independently for two or more radiation sources. And the rule says if the two thicknesses, X1 and X2 here, differ by more than 1 TVL, then the more penetrating, 1 TVL of the more penetrating radiation, then use the larger thickness. So if that's the case, it's very simple. But on the other hand, if they're not different, if they're less than 1 TVL in difference in their values of their two thicknesses, then you need to add 1 half value layer, or 0.3 TVL, to the more penetrating radiation thickness, barrier thickness, whichever it is, the larger thickness. For example, if you find that a minimum barrier thickness required for a 6 MV beam, and then you find another for the 18 MV, and you combine these two thicknesses to get the total thickness required, minimum thickness required for the barrier. And if you have more than 2 sources, which is not uncommon these days, you need to apply this thing more than once, this rule. All right. How do we estimate the primary leakage radiation workloads per week? The primary barrier workload per week at 1 meter from the X-ray target is typically estimated this way. You take the total number of treatment sessions per week times the average dose at isocenter per treatment, and that product gives you the workload. For example, if you had 30 treatments per day times 5 days a week, that's 150 treatments per week. And the average dose at isocenter was, say, 180 to 250 centigrade, and we took 225 as a representative centigrade. Then, and I've got a little note here that's saying that we really want the dose delivered at isocenter under Dmax buildup. That's really what that dose should be. So the primary barrier workload would be 150 times 225 centigrade per week, or 338 gray per week at 1 meter. And you typically would round that up a little to, say, 350 gray meter squared per week. For photons, since a gray and a sievert are numerically equivalent, you could also express this as the same value in sieverts or millisieverts. How do we estimate the radiation leakage workload when, let's say, 60% of the patients are treated with IMRT or rapid arc? If we use the modulation factor at 4, which is pretty representative of what people have found, and the fact that the F in our formula was 0.6, we plug in and we see that basically our primary barrier workload times 0.4 for the unmodulated and 0.6 times 4 our CI value for the modulated beams, and we get 2.8 times the primary barrier workload. So rounding up a little bit, we have 1,000 gray meters squared per week, which is about 50 times higher than our primary in terms of, not 50 times, it requires more shielding. I'm sorry, I'm off track there. So if we use our leakage, maximum allowed leakage factor, F, then F times WL is actually 1 gray meter squared per week, which is a lot less than the 350 we had for the primary. So secondary barriers are significantly thinner than primary barriers. All right. If we take these two workloads we've just calculated, how would we get the number of TVLs that are required? So let's assume that our use factor for the primary barrier is 0.25, And the distance from the isocenter is 3.5 meters, and the occupancy factor is 1. And the area is unrestricted, so therefore our design goal is 0.02 millisieverts per week. We plug these into our primary barrier factor, and here I usually do this. I'll take the distance from isocenter to the location and add 1 meter from isocenter to the X-ray target. But we plug that in and we come up with 4.63 times 10 to the minus 6 as the required maximum barrier transmission factor. And take the log of that 1 over B, and that gives us a number of TVLs, which is 5.33 TVLs required. For the leakage radiation, plugging into our formula and using U equals 1, we get 2.45 times 10 to the minus 4 for our maximum barrier transmission factor, and 3.61 as the minimum number of TVLs. So again, here we're seeing that the difference between these two is really about a factor of 50. So more attenuation for the primary, as one would expect, by about a factor of 50 in terms of attenuating properties. So we're done with this little second section here, and we have yet another question for Christina to manage.
All right, great. Thanks so much, Jim. So the poll question is live. And for those of you who are just joining us, this may be your first poll question. And if it is, go ahead onto the left-hand side of your screen and make sure to enter in your answer that you would like to give. And Jim, if you would like to go ahead and go over the question, we'll just take about a few seconds after that, give everyone a chance to weigh in, and then we'll go over the answer.
Okay. If a therapy center uses 100% IMRT and or rapid arc for treatment delivery, by what would you expect, it's kind of poorly worded, what would you expect the ratio of WL to W primary to be? We've got 1, 2, 4, 8, or 12.
All right, great. So I'll just give everyone a few more moments to go ahead and answer this question. And as Jim mentioned before, the questions 6, 7, and 8 are extra questions. We have about 4 sets of questions throughout the webinar. We're just going to do the first question in each set. All right, Jim, it looks like most people have had a chance to go ahead and weigh in on the poll. So why don't we go over the answers?
Okay, well, the correct answer is C4, because when you have 100% IMRT, it's just basically the CI factor that is involved in multiplying the primary barrier workload. So that ratio would be 4. Just before we go on, I want to point out question 8 down there. It's for a 10 MV X-ray beam. The weight of a concrete primary barrier will be the same as an equivalent in terms of shielding and thinner lead barrier. Is that true or false? And the answer is true. It'll be the same, because it's pretty much, for 10 MV, you've got a dominance of Compton scattering, which is really only dependent on the total mass in between the barriers. So you would, when you calculate, be it concrete or lead, you'll end up with essentially the same mass, i.e. same weight. Okay. And here's a couple more questions. We'll have to skip right now, but if if you have a chance to come back and look, they're typical exam questions. All right, radiation sources and how they attenuate in various materials. I think that's the next logical step before we get on to applying all this stuff. Uncharged radiations, particularly photons and neutrons, attenuate roughly exponentially with path length, t, through a barrier. Broadbeam attenuation has been evaluated, and the recommended TVL values are tabulated in NCRP 151 for standard shielding materials. And there are other sources out there, and if you find a unique type of, let's say, source, shielding materials, if you find other needs, you can usually search through the literature and get a pretty good idea of what to use. Sometimes you have to resort to Monte Carlo to determine the characteristics of a particular barrier material. Now, the most important thing here, I think, in terms of clarification of what we're talking about, the barrier thickness, I give a label X, and it's the thickness, whereas the path length along which the beam going this direction passes is T, and at a angle of incidence beta, we then have a simple relationship that the path length is equal to the barrier thickness divided by the cosine of beta. So our shielding inverting our B values to get thicknesses. We actually if we're at a angle of incidence that's other than 0, we're determining the path length, and then we in turn get the thickness from knowing the angle of incidence. Okay, back to what does transmission data look like. It typically looks something like this, where the log of the barrier transmission factor has got a slightly different thickness of material for the first segment to go down by 1 TVL, then to go down by another TVL. These, in this example, our first TVL is 30 units, the second TVL is 20, and these subsequent ones are 16. So we often break a barrier transmission curve like this down into 2 components, sometimes 3, where we use a first TVL and then a equilibrium TVL. In this example, that would be 16. And we do our calculations knowing these 2 values, tabulated values. In some materials and some types of radiation, a single TVL value is good for the whole curve. NCRP recommended values are based on review of all the literature out there and basically come up with values that are on the conservative side. So for 6 MV and 18 MV, this is 18 is based on BJR supplement 11. That's the older classification of beam quality. You would call it 23 today in BJR 17 specifications. But these 2 beam qualities listed here, the primary beam barrier TVL1 and TVL equilibrium are listed here. And you can see a slightly larger value for the first versus the equilibrium in most cases. In lead, they're the same. There's no difference. Steel, pretty much the same. Leakage radiation is a little less penetrating, but not a whole lot, and so slightly smaller TVLs than the primary. Okay. Also, I'll be referring to normal density concrete. I didn't explain that, but normal density concrete is what's called ordinary concrete or normal density concrete, and has a density of 147 pounds per cubic foot or a specific gravity of 2.35. Anything Heavier than that is usually referred to as high-density concrete. And many contractors have to be urged to make their concrete 147 pounds per cubic foot, which is what we calculate on, because it isn't guaranteed the contractor will do that unless you tell them they have to. All right, so how do we use these TVLs to obtain the barrier thickness? Once we have calculated the number of TVLs, there's basically two formulas we can use. One of them says that if the number of TVLs required is greater than 1, then the required minimum thickness or path length is determined by taking the first TVL plus n minus 1 times the equilibrium TVL. So the number, if this is the first TVL, this is the remaining number, the remaining number of TVLs. And that's the formula we would use for normal incidents. For normal incidents, the T would be just the thickness. At any other angle of incidence, we would be calculating the path length, and then in turn using this formula down here to get the barrier thickness. If we have one or fewer, less than 1 TVL required, then it's just the fraction of the thickness of 1 TVL. All right, use factors. There's a lot of data that's come out over the years, people monitoring their gantry orientations and seeing that beams point here and there and have all kinds of variations across the barriers. But I think it's highly recommended to stick with the simplest values, and that's basically each barrier gets about 1/4 of the total workload. Now, sometimes I'll use 0.3 for downward pointing the floor because you're doing an awful lot of work, hopefully doing your QA and annual calibrations with the beam pointing down. But an upward is slightly less common, so it's 0.2, but basically 0.25 as a barrier use factor is what is recommended. Now, IMRT and Rapid Arc do spread out the beam in more different oblique directions, but to be ALARA, 0.25. If you're using your room for any kind of total body irradiations, then you have to really be careful because they can greatly affect the use factor for that particular barrier behind your setup stand. And you have to be real careful about that. All right. The fraction of the clinical work week that an individual is in an area being protected, it's called the occupancy factor. NCRP has some suggestions for these values. And this table, I hope you can read it, it's kind of small, but anyway, it gives you, okay, if this is a fully occupied area, administrative clerk, treatment planning area, whatever, use a full occupancy. If it's a hallway, employee lounge, staff rest area, you might take a 1/5. And generally, when you're designing a radiation shielding plan, you want to know the area, have a pretty good idea what it is, and you will probably be able to come up with even better, more reliable recommendation or values to use for your occupancy factor. And you have to keep in mind, too, that the area may change. I remember shielding a place that had a storage closet for a room near the vault. And they asked me a few years later to come back and review it. for their new accelerator going in. And I said, well, is that storage closet still there? Oh, no, that's now an office. Ah, well, that, so you do have to be careful that things do change, and it's always better to be on the safe side up front, because they ended up having to put some extra lead in that barrier just to meet the fact that it was now an office. All right, and I also put down here at the bottom that be careful about using this 1/40th value as an occupancy factor. In fact, there was a lot of debate in NCRP about whether that should be on there. And the reason is that that's basically 1 hour per week. It means an individual there could receive an awful lot of radiation in 1 hour. And that might go over the public limit. All right, so let's look at an example here for a 6 MV beam. I know there was some request to have 6 and 18, but it's too involved to do in the time frame we have. Consider a therapy room with a 6 MV X-ray beam, treating 35 sessions per day with an average dose to the isocenter of 2 gray. The primary barrier has a use factor of 0.25, and the room on the other side of the barrier is a transcriptionist office. Given the layout below, we're going to see in a minute here, how much normal density concrete is required to protect the transcriptionists? Let's go down here and take a quick peek at this. So we've got our primary barrier here, secondary barriers, and here's the point we're looking at right now, just on the other side of that primary barrier. The office is here, uncontrolled public occupancy, public limits. All right, we'll come back to this figure in a moment. So the primary barrier workload at 1 meter is estimated as follows. You take 35 treatments a day times 5 days a week times 2 gray average dose per fraction, and I'm going to divide it by the TMR 0.67 for an average depth of 10. So I end up with basically 522 gray per week, or 5.5 times 10 to the 5th millisievert meter squared per week. The area is uncontrolled or unrestricted, and therefore our design goal is 0.02, 1 divided by 50 millisieverts per week. So setting our design goal equal to the primary barrier transmission factor, WUT over D squared, we calculate, put in the values, and calculate. We end up with 1 over B is equal to 1.91 times 10 to the 5th. So the minimum number of TVLs is a log of 1 over B is 5.28 TVLs required as the minimum number of TVLs to shield that area. And from NCRP 151, we find that for 6 MV, again, the TVL1 is 37 centimeters and TVL-E equilibrium is 33. And we plug into our thickness, assuming normal incidence, formula, and we get a total of 178 centimeters, or 70.2, a little over 70 inches of normal density concrete. And for ALARA, we would then round that up to 72, which really means 183 centimeters, and we go back and recalculate how many TVLs do we get out of that, and it's slightly up to 5.42. And that's what we would specify is how many we need, how many TVLs. So I want to point out here that in the USA, barrier thicknesses are most always specified in feet and inches, with a 3-inch increment is kind of the smallest one they like to deal with. They'll do otherwise if you twist their arm. And when metals are involved in shielding, usually it's to the 1/2 inch. If it's lead, it might be to the 1/4 inch. All right, so now we've got our primary barrier. What about the secondary barrier? The current radiation oncologist in this facility thinks that she's going to use IMRT for only 40% of her patients, and there's no rapid arc. But we know that that could increase in the future. We might even get another radiation oncologist. So let's increase it at least to 50% IMRT. And even that might be a little on the low side. But anyway, that gives us a little hedge. So our workload for leakage is going to be 0.5 for the unmodulated beams and 0.5 times 4 for the modulated. We end up with 13.8 times 10 to the 5th millisievert meter squared per week. All right, and then an important question to ask here is, where is the calculation point for the secondary barriers when you've got leakage coming from one area and patient scatter possibly from another or slightly different area? This point we're looking at is right next to the primary barrier. And the leakage radiation comes right along here, just missing that edge of the primary barrier. But the scatter radiation starts at the isocenter in the patient and goes off at a slightly different angle. So our calculation point for the two is really this location, but we're going to assign a scatter angle of theta, which turns out to be 26 degrees in the layout here for the scatter radiation, and this angle for the leakage radiation is only 21 degrees. So there's slightly different geometries, as you can see. But this is really, this location is going to get a fairly energetic scatter radiation beam to be added to the leakage radiation. All right, and that's pretty much what I said here in this down here, that we use 26 degrees for scatter and leakage radiation is incident at 21 degrees. And the common distance from the isocenter to that location is 5.6 meters. And how do I get this? Excuse me. How do I get this number? This comes off the architectural drawings. Everything comes off the architectural drawings. Those are fundamental to doing any of this, is having a set of drawings that you can read and get distances off of accurately. Okay. So what does the leakage radiation contribute to this point just off the primary barrier? All right, we go back and we put in to our formula the data that we have here, that the leakage radiation workload is 13.8 times 10 to the 5th. It's a uncontrolled area, unit occupancy, U is 1, and the distance is 5.6 meters from the isocenter. And we get 2.2 times 10 to the 3rd is our 1 over b. So the log of that is 3.34. We need a little over 3 TVLs. So the minimum path length would be 102 centimeters, plugging in these values again from NCRP 151. Scatter. All right, now here's where it gets interesting to me, is that when you look for the scatter data at 26 degrees and interpolate the table there, you find that the scatter fraction is actually 42.4 times 10 to the minus 4. And the TDL for this is 27.8, which is pretty high. It's comparable to leakage radiation. And most of the time, your scatter fraction, is more like 10 or lower times 10 to the minus 4. So it's higher fractions scattered in that direction and a higher quality. So taking our field size to be 20 by 20, we go back to our formula from before of the scatter radiation calculation. We have our primary barrier workload, because that's what's incident on the patient, times the use factor, which in this case, the beam is pointing in the proper direction to be scattered at the angle we said, 26 degrees, only 25% of the time. Plug in the other values and calculate, and we get 9.3 times 10 squared, or almost 3 TVLs, but 2.97 TVLs. When we put in the fact that our TVL is 27.8 centimeters, we need 82.5 centimeters of normal density concrete just for scatter radiation. So now we do this two-source rule. We take the difference between leakage and scatter thicknesses, it's 19 centimeters, which is less than 1 TVL. So that means that we need to add a half value layer of the leakage radiation TVLs, leakage radiation, to get our total thickness. So we take the 102 required for leakage and add another half value layer to it, and we end up with 110.7 centimeters instead of 102. We've increased because we have a significant amount of scatter radiation coming to that location. All right, so if the fact that the scatter and leakage are coming at an angle are taken into account, what is the actual barrier thickness required? Now we use this cosine of beta to multiply our path length, minimum path length, and we find that with the cosine of 21 degrees, we have 103 centimeters or 40.7 inches. And again, we'd probably round it up to 42 inches, 3.5 feet. All right, that was a mouthful. Let's go and now ask another question. What happens if the secondary barrier point that we're looking at is at an angle of 90 degrees? It's on a different barrier at right angles to the one we're talking about, just got through talking about. And let's see, it's up, this barrier is up here at 90 degrees, or on the bottom side. So what happens at 90 degrees with respect? Well, pretty much, if we keep the distance as 5 meters the same, and the same occupancy factor, and keep the areas uncontrolled, assuming everything is the same, the only difference is the scatter angle. So as before, the leakage radiation is going to come out, should come out the same, keeping the same distance. For scatter, on the other hand, now we have a order of magnitude smaller scatter fraction, and the TVL has gone from almost 28 centimeters down to 17. And in this case as well, we get 90 degree scatter no matter what orientation the gantry has. So our use factor is 1. Whether the gantry is pointed up, down, horizontally, there's always 90 degree scatter going toward that barrier. So the number of scatter TVLs required turns out to be 2.67, and the scatter thickness, the thickness for scatter is 45 cm. Oops. So the difference between our two thicknesses is 59 centimeters, which is greater than 1 TVL. So we really only need to use the smaller, the larger TVL, 104 centimeters, 104.8, as that's it, no additional. So again, we would round this up to 42 inches of normal density concrete. And the main difference here in this particular barrier is that it's determined by the leakage radiation, whereas the other barrier right off the primary, the secondary barrier, was by and large determined its total thickness by the scatter radiation contributing significantly. Okay, now we're going to change and direction here just a little bit and ask what happens if we've got a dual energy machine or even a more modern 3 energy LINAC. For each energy, you need to determine their respective workloads the best you can. And sometimes that'll depend on the radiation oncologist's preferences and how they do things. And that could change in time, so be careful about doing that. And their delivery techniques, again, that's something that can change with time. So you have to be careful and be conservative and, you know, kind of a worst case situation. Okay, let's say we go to 80% IMRT and so on. And do we use 6 MV for IMRT only, or are they going to do IMRT with 18 MV? Important questions to be asked. So now we're going to independently calculate the minimum barrier thickness for each beam, and then we're going to combine those results according to the 2-source rule. We'll do it for the 2 different energies, or if there's 3 involved, we'll repeat it and do it again for all 3. So each time our barrier is going to be the more conservative thickness out of the possible combinations. Another important factor for a higher energy beam being greater than 10 MV, photoneutrons are going to be produced above 10 MV. They're actually produced at 10, but they're not very significant. But they're certainly important at 15, 20, 23. And you have to be careful about your shielding materials because some materials don't shield neutrons very well, such as lead. You need to avoid or minimize materials that can be neutron activated. And you need to account for capture gamma radiation, which results when thermalized neutrons are absorbed, and particularly by hydrogen. So I mentioned neutron activation. High energy machines do activate some of the material in the room, be it concrete or other materials that might be in there. Now it's fairly low activation at 15 MV, a little higher at 1823, and it can be very high. And the machines of yesteryear no longer out there, but I once worked with a 45 MV Betatron, and you could walk in the room with your neutron meter and your radiation meter, just looking at the survey from X-ray photons coming out, gamma rays, and it was measurable, highly measurable. In fact, they preferred to not do any work on the machine until it had a few hours to cool down. But in modern day, relatively lower energy machines, there's really no reason to be concerned about walking directly into the room or after the beam goes off, unless you had a real long irradiation. I mean, you gave 10,000 monitor units, you might be a little concerned there. And there are materials in the head that do get activated. All right, now, once we get all these calculations done and say we want barriers of this thickness and that thickness, how do we evaluate if this really meets all the considerations? And furthermore, if the radiation inspector comes through, he's going to measure generally an instantaneous dose rate on the other side of the barrier. And we should be able to tell him what we expect to see on the other side of the barrier so that he's not, let's say, flabbergasted by the relatively high reading that's on there momentarily. And so we can make these estimates and provide them in a shielding report or have them available for the inspector. One of the first questions they ask are the public areas shielded sufficiently to satisfy the constraint that's put on public areas, namely that the time, you probably heard it expressed as 2 millirem in any 1 hour coming from the NRC. And this constraint still applies to accelerators and through the suggested state regulations. So we have to be able to demonstrate that 0.02 millisieverts in any 1 hour is satisfied. And the way that is done, at least the way NCRP 151 recommends that it be done, is to calculate this time average dose rate in any 1 hour called RH, time average dose rate in any 1 hour. And it's calculated from the time average dose rate per week times a factor which is M over 40 hours per week. And this M is the ratio of the maximum number of patients that could be treated in any 1 hour to the average number per hour. The maximum number is basically our best and most conservative estimate based on, let's say, well, you can't get more than 6 treatments in there in an hour. And if you were really pushed, you might do 8, but you certainly couldn't do 15. So we'll use 8 in an hour. And the average is based on the workload, actually the radiation workload. But you get the total number of patients per week, which we already know, and divide it by 40 hours per week. That gives you the average. And then that ratio gives you the M, which goes in here. It's an enhancing factor. So that RH is used to make that assessment. This should be less than 0.02 millisieverts in any 1 hour per hour. RW, on the other hand, the time average dose rate per week, is the quantity NCRP recommends to compare with the T over T ratio, or you could say RW times T should be less than or equal to P. RW is computed, it's discussed in NCRP 151, but the simplest method I use is to calculate it using the instantaneous dose rate on the other side of the barrier with the shielding in place times the time the beam is pointed toward that barrier per week. And that would give you what's called RW for a primary barrier in this example here. The IDR is just the barrier transmission factor times the instantaneous dose rate at isocenter, 1 meter, divided by the inverse square, distance from target to the location. We know this, oops, keep hitting this. We know what this is, we know what that is, the manufacturer tells us, and we know this. So we can get the instantaneous dose rate on the other side of the barrier, put that in here. And the time the beam is pointed toward that particular barrier is our primary barrier workload times the use factor for the primary barrier in question divided by the instantaneous dose rate at isocenter. That gives you the number of minutes per week the beam is on. It's nice to calculate this way because this is what the inspector should expect to have as a weekly dose when he measures an instantaneous dose rate of this value, if you can give him these values, then he can say, oh yeah, that's RW is less than whatever the limit is for that particular area. So, kind of summing up that our RW value is to be compared to P over T ratio, and our RH value that's been computed should be less than 0.02 millisieverts in any public area. All right. Coming up for air, we got a question here, Christina.
Okay, great. Well, for those of you who haven't had a chance to answer a poll question, now is your opportunity to do so. It'll be available on the left-hand side of your screen. And while you go ahead and answer that question, Jim, I just want to let you know that we are coming up. We're about an hour and 20 minutes into the webinar. We were hoping to get it wrapped up in the next 10 minutes or so. So we have a couple of options here. Looks like you have about 20 slides left. So we can either kind of breeze through that last section there and try to get it all in, or we can save it for a sort of follow-up webinar that we can let everyone know about and set a time after this and send out an email to everyone. And then we can kind of move on to Q&A if you feel like this is a good stopping point.
Yeah, it is pretty close. I think I could breeze through those to at least give everybody a quick look.
Okay, sure.
Yeah, they're a little lighter and less involved than what we've gone through so far.
Okay, sounds good. So we're going to just sort of breeze through the last portion of this, hopefully try to wrap it up before 8 o'clock, and then we'll see if we have time for Q&A. So it looks like some folks are still answering the poll here, so we'll give you just a few more seconds to go ahead and answer this poll question. And Jim, you can go ahead and read the poll question.
Okay. Which provides the most shielding? 1 TVL of concrete, 3 half-value layers of steel, 0.7 TVL of concrete plus 0.5 TVL of earth, or 1.4 TVL of lead. And the answer really doesn't depend on what the material is, it's the total number of TVLs. And 1.4 TVL is provides the most shielding.
All right, great. Looks like most people had gotten that answer.
Okay, good.
All right. Well, thanks for taking the poll, everyone. I'll let you wrap it up here.
All right, we will move rapidly.
Okay.
All right. One of the more complicated things to deal with in this is doors and entrances and HVAC penetrations. And we can't go into all the details on that, but I want to give you a quick overview. Let's take a quick look here at this 2 different kinds of layouts here. On the left, we have a mazed room with a maze barrier, and there's 2 rooms that are basically identical, mirrored. And a relatively thin door here because the maze barrier provides a lot of protection for that door. This is called a mazeless room or a direct access, and it's a so-called also direct shielded door where there's no maze to protect, and the radiation coming from isocenter and around isocenter can come straight into the door. So this is a thick door, and it's usually a sliding door, too heavy to be on hinges. So that pretty much says what we have to say there. For low energy rooms, that is no higher than 10 MV X-ray beams, there's a formula in NCRP 151 that basically says how to calculate what is reaching the door behind a maze. So this is a maze room calculation, and it involves several types of radiations to get to the door. There's the primary beam that's scattered off the barriers and then back to down the maze. There's leakage radiation that's scattered off the walls and down the maze. Patient scatter that also scatters from the wall and down the maze. And finally, leakage radiation that is transmitted through the the maze barrier. And this is probably the most important because it's the most high energy. These radiations are at least double scattered and relatively low energy. So that's all I want to say there, but usually it doesn't take much in the door to shield these radiations. 1/4, 3/8 inch of lead is usually sufficient. And if you don't go above 10 MV, the picture is complete. But once you go above 10 MV, photoneutrons need to be calculated and determined, and they produce a fair amount of radiation that's hard to shield. So you'll end up with a thicker door, even with a maze, and it requires some hydrogenous materials, i.e. borated polyethylene, to attenuate and absorb photoneutrons, and it requires lead to attenuate the capture gamma rays that come from all these photoneutrons. So here's the picture, and all kinds of radiations scattered around for low energy beams come down here, but with the high energy beams, the neutrons scatter all over the room and wiggle their way down here, coming from all over the room. They exponentially attenuate as they're going down, their fluence, but there's capture gamma rays produced that come to the barrier, and neutrons. So it's basically a complex calculation, and I don't want to say much more about that. The direct shielded doors, even more challenging. And some examples of some direct shielded door thicknesses. Here's one that was a 15 MV and had 24 inches of high density concrete, basically double the density of normal density, and it required 280 grams per centimeter squared of thickness shielding material. And an 18 MV that was shielded with a 9 inches of lead and 4 inches of borated polyethylene. So they're big, heavy doors, tens of thousands of pounds. One question that comes up from time to time: what about photoneutrons and secondary barriers? It turns out if you can shield for the leakage radiation, X-rays, typically takes 40 inches or more of concrete, that is sufficient for photoneutrons. So secondary barriers are pretty well accounted for by if you're using concrete. If you're not using concrete as your secondary barrier, you better be careful because lead or steel don't attenuate photoneutrons nearly as well. HVAC, I know we're got 1 minute to go here. HVAC, basically heating, ventilation, and air conditioning, has to get into the room somehow. So there's typically a opening in the barrier that's 10 inches high and 18 to 24 inches wide. And if that is like 8 feet above the floor, you could still get a significant amount of radiation coming through. Now, if you have a maze barrier in the room, then you put the openings above the door, and the maze does the attenuation of everything, and you get very little, but some, coming out. Typically, photoneutrons will come down and come out, but it's up 8 feet above the floor, and generally it's fairly easy to shield if there's anything measurable there. In a mazeless room, these HVAC penetrations are very significant and require a fair amount of work to figure out how to shield them and keep it under cost. All right, I see our time is up, but I'm going to just go real quick HDR rooms, not part of 151, but NCRP 155 in the Appendix D has a real nice summary of how to calculate the workloads and the barrier thicknesses for an HDR room. It's very, very clean, straightforward, and I recommend you go there. If you're an APM member, you can get this report for free, and it's very nicely done. SRS, SBRT. Workloads go up, and if they're a dedicated room, you need to work on your workload. They'll be a lot higher. The CyberKnife. An example is in NCRP 151. The main difference is that the beam points all over the place, and every barrier is really a leakage barrier and a primary barrier, except for the ceiling. The CyberKnife does not point above 22 degrees above the horizontal, and therefore the ceiling is only for leakage radiation. But all the other barriers are primary and leakage. Use factors are low because there's many beams involved in a plan. And other thing is calculating the workload. The machine is calibrated at 80 centimeters from the X-ray source. And when you're treating with cranial treatments, that's the way it is. But for extracranial, the actual treatment distance varies from 90 to about 110 centimeters. And so there's a difference here. It has a lower workload at 1 meter. So how do you combine these two workloads for cranial and extracranial? Well, you bring that factor into account of 0.8 squared, and you combine the cranial times 0.8 squared plus the extracranial workload at 1 meter to get the total workload at 1 meter. And that's an important step in the process. Okay, tomotherapy, only one thing I want to say is it's heavily modulated. The CI for tomotherapy is 15 to 20. And proton machines, I won't say anything because I'm way over my time, but neutrons are what are being shielded for in a proton machine. The protons are easily attenuated and rarely even make it to the barriers. Neutrons are flying all over the place, and they interact with all the walls and pretty much become isotropic in the room. And all barriers have to be shielded with fairly thick amount of thicknesses of concrete, anywhere from 6 to 10 feet. And it's the neutrons, though, that are the problem. All right. I guess we probably won't get into this, but I'm done.
All right. Well, thanks everyone for sticking with us, and thank you, Jim. And I have the poll question up, so if you're still with us, you're welcome to go ahead and weigh in. And I'd love to squeeze in this question, and also we have a few questions for Q&A. If you'd like to stick around, you're welcome to. We're going to just take a few minutes to go over those Q&A questions after this poll. All right, Jim, if you want to just go over this question, that would be fantastic.
Okay. What materials typically go into a high energy, greater than 10, entrance door? Lead and steel, lead steel paraffin, polyethylene and lead, borated polyethylene, lead and steel, or just lead?
Okay. The answers are rolling in. Just give everyone a couple more seconds to weigh in on the poll. All right, Jim, would you like to go over the answer?
Yes. Well, it's basically borated polyethylene, lead, and there's steel. I didn't mention it, but steel in the door. So those three are the typical materials.
All right, great. So we just picked a few Q&A questions from the chat room. And the first one was, have you ever taken a neutron meter on the roof of a vault? Do you need to? Can you go over this quickly?
If it's a high energy machine, yes, you do. Yes.
Okay, great.
And
Second.
yeah.
Oh, sorry, I didn't know if you had anything else.
No, that's fine. That's fine.
Okay. The second question, should we wait a few minutes before entering the room after exposed with photon 15 MV?
Yeah, I think I answered that. I saw that question come up, and no, generally not. But if you wanted to work on the head of the accelerator, you're an engineer, you might want to wait a little bit because there are materials that do get activated.
Okay, great. Thank you. Just a couple more. Is it recommended that a sample of the concrete are analyzed for density for confirmation?
Yes, it is.
Okay, very good. And if you want to use PB or steel for shielding, can it be in front of the beam, or is it necessary to put a concrete layer between the beam and the material?
I guess that depends on whether there's photoneutrons in the room. And if there's photoneutrons, often we sandwich first with a lowered the concrete to basically attenuate down, as well as get the neutrons down as low as possible, and then follow up with lead to take care of the capture gamma rays. And you might even follow up again with some more concrete, but it's usually attenuate first, thermalize really neutrons, and then take care of the capture gamma rays with the lead.
Okay. Well, thank you so much, Jim, for taking the time to present this webinar, and thank you all for joining us for this free event hosted by WePast. If you'd like to join us for our next free webinar in the series, it'll be on surface-guided radiation therapy on Thursday, March 30th at 6:30 p.m. with speaker Mike Talmer, the Chief of Radiation Physics at Centura Health. And if you'd like to get more information on up-to-date webinars, you can follow WePast on Facebook, Twitter, and Google+. And if you'd like to make a recommendation for future speakers, you can contact me directly via email at christina@wepast.com, or you can take this short survey. All right, thank you all so much, and good night.